So last week we introduced sampling distributions. Remember a sampling distribution. We have a population. We take a sample of size n. We throw a value on a dot plot. We do that over and over and over and over and over and over and over, blah, 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 until we have a sampling distribution of values. Okay? So what we're going to do is today we're going to focus on proportions. We're going to focus on doing p-hats.
How we would guess the proportion of the amount of a thing within another thing.
Yes.
So you were telling me that effectively we are learning this so that we can more effectively win school competitions.
Yes. Perfect. So, basically, again, remember, think about we have a population up here. And in this population, we have a proportion of something. Maybe it's the proportion of students that have brown hair, the proportion of students that wear glasses, the proportion of students that drive, the proportion of students that, I don't know, have 4 TVs in their house. Like, this is just whatever, okay? It's a proportion of something in the population. And we take a simple random sample of size n, simple random sample of size n, and from the population and in our simple random sample, we would calculate p hat. So we would find what proportion in the sample have brown hair, what proportion in the sample wear glasses, what proportion in the sample do whatever it is we're talking about, and we find that p hat, and then we stick that on a dot plot.
Do I need to watch yesterday's lesson before I do
Nope, you should be right here with us. And then guess what we're going to do? We're going to repeat that over and over and over again until we create this sampling distribution that is full of p hats. So what have we done?
What have we done?
We chose an SRS of size n from the population with size capital N. The population size is capital N. The sample size is little n. In the population, there is a proportion of success of P. That is a proportion of whatever it is we're looking for. Most of the time, we don't know that answer. We don't know what that is.
Does that say N or R for the first?
N. Most of the time, we don't know that population value. And then we calculate P hat from our sample proportion of successes. That's just the words to go with the picture that I just drew. Now, what is the resulting mean of this new distribution full of p hats? The mean of p hat is simply equal to the population proportion. Last week we did a little example where we had this bag that had imaginary marbles in it. Half of them were red, half of them were blue. And we took repeated samples of size 20. And we calculated what proportion were red. And at the end, over here on the far right, we had a distribution that showed that the true population value should have been 0.5. And when we looked back to the true value, it was truly 0.5. So our p hat distribution should center around the true population value. And that's how we know that the mean of p hat is truly equal to the population proportion. The mean of this p hat distribution should equal the population value, okay? If you guys look on your formula chart, if you look on the back side of your formula chart, you will see across the top it says random variable for one population p hat, and then it says parameters of a sampling distribution. The mean of p hat is right there. It's p. Now, the standard deviation of p hat is also on your formula chart. It is the square root of p times 1 minus p divided by the sample size. This is on your formula chart. P, again, is the population parameter or proportion. N is the sample size that you take out of the population. Now, there is one little catch with this particular formula. You do need to check something called the 10% condition when you are using the standard deviation of a sample distribution of p hat. You need to check this thing called the 10% condition. What the 10% condition is I need to make sure that 10 times the sample size is less than the population size. Now, the crazy thing here, guys, is that most of the time you're not going to know how many people are truly in the population. You're just going to know it's a population of a large school or a population of a large city. And so this is going to end up being like an assumption, basically. The reason behind this has to do with making sure that we have a good representation without having like a biased section of the population. And so we have to make sure we have enough, but not too many, because at some point you start to have little pockets of bias. We will talk way more about the 10% condition in next chapter, but for now, just know anytime you're working with the standard deviation, you're going to be asked to check the 10% condition. We'll do 2 examples today, so you'll get a chance to see them, okay? All right, so we have our p-hat distribution, we have the mean of our p-hat distribution, we can calculate the standard deviation of our p-hat distribution, and the only thing really that we need to do is to see what shape it is. What is going to happen to the distribution of p-hat if I increase my sample size? What happens to the p-hat distribution if I increase my sample size?
It increases.
What increases?
The p-hat distribution, like the range of it, wouldn't that increase? Oh, sorry, the overall distribution is the average, right? Mm-hmm. Decrease, sorry.
Okay, so the mean of the distribution, the actual middle of the distribution of p-hat stays the same. So remember the Reese's Pieces machine that I showed you guys on the board last week? When we increase the sample size, the mean was still 0.5. That didn't change. But the standard deviation changed. And in fact, the standard deviation of p-hat decreases. Anytime you increase your sample size, you're decreasing your variability. You've got a better representation from the population, so you're going to be more centered around the truth. Okay? Now, if I go to the population and I take a sample and I find the p-hat and I stick it on a dot plot, is that an approximately normal distribution? No. So I'm going to go do it again and I get a p-hat. Is that approximately normal? No. And I do it again and I get a p-hat. Is that approximately normal? No. Is this approximately normal? How about this? Do I have approximately normal yet? Kind of. How about now? How about now? When do I get approximately normal? So that's what this question is asking. At what point do I have an approximately normal distribution of p-hats? There is a point where you get that. And that has to do with your combination of your n, your sample size, and your proportion from your population, your p.
Did you just say that it's after n number of times?
Sort of, ish. So, when the large count condition is met, that is when you have an approximately normal sampling distribution. When the large count condition is met, that's when you get an approximately normal p-hat distribution. So, what question do you have for me? What's the large count condition? As long as my sample size times my population proportion is greater than or equal to 10, and my sample size times the complement of my population proportion is greater than or equal to 10.
What is like the complement?
So 1 minus p.
Okay.
So p is my population proportion. 1 minus p is the complement of that. So let's say the population proportion is 50%, the complement would be 50%. If the population proportion is 20%, the complement would be 80%.
Oh.
If the population proportion is 40%, the complement is 60%. Let's say P is 10%. What is the complement of 10%?
How much would you add?
So 1 minus the, you're trying to get to 100%. So if this is 10%, what does that have to be? 90. That's the complement. Yep. So here's the good news, you guys. Most of the time, this works without any problem. But sometimes if your population proportion is really low, like 5% or 1%, then that's when this starts to be a problem. How do you think you can fix it? Increase your sample size. Then you will get a more normal distribution. I'll show you some pictures in a minute that will sum this up. All right, so we have our p-hat distribution. We know how to get the mean. It's the population value. We know how to get the standard deviation. We use the formula. We know how to make sure that the 10% condition is met. We know how to make sure that it's an approximately normal distribution. And that is all of 7.2.
Wow.
Now we're just going to practice doing it. And I'm going to show you why you care.
Can we eat the seed, dude?
Oh, sure. Let's do it. All righty. About 75% of young adult internet users age 18 to 29 watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion of p-hat in the sample that also watch online videos. Now, what should it be? When I take 1,000 people out of the population, what percent should be watching online
75.
videos? It should be 75%. Because the population value is 75%. So if the population has 75% watching online videos, then when I take a sample of 1,000, I should get an average of 75% watching online videos. Okay? So the mean of the sampling distribution of p-hat is just equal to the population proportion, which was given to us in the problem, which is 0.75. The mean of p-hat is just equal to p, and that's 0.75. How do I know that? Because the formula says so. That's how I explain it. I write the formula. Yay. Now we're going to find the standard deviation of the p-hat distribution by using the formula square root of p times 1 minus p over the sample size. I know p and I know n, so I can just plug and chug here. The square root of 0.75 times 0.25 divided by 1,000. This is going to give you the standard deviation of the sample distribution of the p-hats. Now, my sample size here is pretty big, so I should get a fairly small standard deviation because this is a pretty big sample size. 1,000 people, that's a lot of people. So my standard deviation should be fairly small. So go ahead and plug this in and find the standard deviation of the sampling distribution of p-hat. Calculators, remember I said get those out? Yeah. Oh, cool. Okay. Yay. What'd you get?
0.01369.
We'll go with 0.0137. Perfect. Now, I do need to make sure that this 10% condition is met. This is basically to make sure that I have a pretty good representation from the population. So, 10 times the sample size has to be less than the population size. Now, this is where it gets a little strange, you guys, because I know that 10 times 1,000 is equal to 10,000. But what is the population size in this problem?
L. Large.
It's large, right? It's a bit. Like, it says young adult internet users age 18 to 29. So, I mean, I'm assuming I'm talking about all young adult internet users age 18 to 29. Do you think that the population of young adult internet users is greater than 10,000? Probably. If I'm talking about all adults age 18 to 29 that use the internet, yeah, I'm pretty sure that's more than 10,000 people. That's probably covered just in McKinney. Okay, so I think we're good.
Did you know more than 3 people use the internet?
That's crazy. No way. So there you go. We have our 10% condition is met. That helps me ensure that I don't have any little pockets of bias. Okay? So I know the mean of this distribution of p hats is 0.75, which it should be. I know the standard deviation is 0.0137. Now I want to see, do I have a normal distribution? In order to find out, we're going to check the large count condition. N times p has to be greater than or equal to 10. N times 1 minus p has to be greater than or equal to 10. Both of these things have to be true in order for me to have a normal p hat distribution. So n was 1,000. P was 0.75. And what is 1,000 times 0.75?
750.
750. Is that greater than or equal to 10? Woo! All right, we're halfway there. Both of these have to be true, so let's check the other one. 1,000 times 0.25. If 75% of 1,000 is 750, then what is 25% of 1,000?
250.
250. Is it a coincidence that 750 plus 250 equals my sample size? No, that's not a coincidence at all. If one of them is found and then I find the complement of it, it will always equal back to the sample size. That's how you can check to make sure you did your math right. So guys, both of these worked. What does that mean? What that means now is that my sampling distribution of p hat is approximately normal. This is great news. This is the best news you could ever have heard. Ever. And now the question becomes, why do I care about this, Miss Lakey? Why do I even care anything about this stuff? Here's why. Because what we do now is we can calculate a probability of a sample being a certain thing. For example,
Oh, we've just determined that this is normal. Oh,
let's
gosh.
say that I want to go out and take a sample of 1,000 young adult internet users. And I want to know what's the probability that I get 70% or less in that sample saying that they watch online videos. It's supposed to be 75%, but what's the probability that it's less than 70%? Well, here's the good news, you guys. We know that our p hat distribution is approximately normal. We know that the mean of this distribution is 0.75. And we calculated that the standard deviation of this distribution is 0.0137. Any ideas what we could do to find the probability that in this normal distribution that we get a sample that is 70% or less?
No idea.
Normal CDF.
Oh my god.
Oh my goodness, y'all. If I want to know the probability of getting a sample, a p hat, another p hat, I go out and take another sample. If I want to find the probability that it is less than 70% in the sample using the online videos, I can just now do normal CDF because I have ensured this is an approximately normal distribution. Here's what we're finding. The probability that a p hat, a sample proportion, is less than 0.7 in this p hat distribution. What's the probability that I get a p hat over here? Yes, ma'am and sir, this is normal CDF. What is the lower boundary of this region?
Infinite.
Negative infinity. What is the upper boundary of this region?
7.
0.7. What is the mean of this sampling distribution of p hats? And what is the standard deviation of the sampling distribution of p-hats?
0.0137.
Boom. And all you have to do, ladies and gentlemen, is plug this into second VAR's normal CDF, and you get your answer.
Why didn't you tell us this on the first day?
I know, right? What? All right. If you think the answer is 1.313, if you think that that's the answer, we should talk after school. Because that would be saying that this little section is 131% of the graph. That there's a 131% chance of this thing happening, right?
Coach told me that.
That means that we don't know what's happening. So, if you see that kind of an answer on your calculator, you should immediately be alerted to the fact that you need to look to the right, like Zane did when he looked at his answer, and see that there is a little e to the negative fourth, which means that this number is times 10 to the negative fourth. So this is actually 0.0001313. Doesn't matter to me. Whatever you like. Here is what I want to make sure you understand. If I know that in a population that 75% of people are supposed to have a certain quality, they're watching internet videos. 75% of people are supposed to be watching internet videos. This is the chance that I go out and talk to 1,000 people and less than 70% of them are watching internet videos. So is there a good chance that I'm going to get a sample that shows that less than 70% are watching internet videos? No, there's not a very good chance at all of that happening. So what do I think if I go out and I get a sample where less than 70% are watching internet videos? What does that make me think? That there was maybe something wrong with my sample. Maybe I had some bias. Maybe I went to an area that has low internet connection. Maybe that's what happened. What else might I think? If it has nothing to do with my sampling was perfect, what else might be the problem?
The person sampling might be wrong.
Say that again?
The person running the original study was wrong.
Very good. That means the original study might be wrong. Okay? So when I get a value that is like, there's a very low chance that this happens, and then I go out and I actually get this result, then that tells me either my sample was bad or the original data was wrong. One of those two options have to be true.
So
Okay.
Can you just write 1 if you were in Mansfield?
Yeah, there you go. Perfect. All right, cool. Very good. Now, what happens to my distribution of p-hats if I talk to 9,000 people instead of 1,000? What would happen to that distribution of p-hats? Would the mean of 75, would that change? No. The mean of p-hat would stay the same. The mean of p-hat stays the same. Whether I talk to 1,000, 9,000, 4,000, 5 million, whatever, the mean is not going to change. It should be the same as the mean of the population every time. But what's going to happen to the standard deviation of that distribution?
It's going to decrease significantly.
It is going to decrease. The standard deviation of p-hat will decrease. Now, here's the fun part. We can actually tell by how much without having to plug it in. The standard deviation of p-hat has this formula. P, 1 minus p, divided by the sample size. That's the formula for the standard deviation of p-hat. If I take the sample and I multiply it by 9, which is how I get from 1,000 to 9,000, then what does that do to my original standard deviation? This is where my pre-cal and calculus students seem to love this question. If I increase n by 9, then what does that do to the overall number, the original overall standard deviation?
Oh, you just multiply by the reciprocal.
Almost. That's almost.
Gosh.
The standard deviation will decrease, but by how much?
The square root of
the square root of 9. Or the square root of 1/9. Sorry. So let me show you. The original standard deviation of p hat was 0.0137. The new standard deviation of p hat will be 1/3 of 0.0137. Now, why is it 1/3 and not 1/9?
Because it's the square root of 1/9.
It's the square root of, and think about there being a 1 right here, 1/9. It's the square root of 1/9, and so that's how you would do it. Now, for those of you who are like, yeah, that's way above my algebra pay grade, that's fine. You could just plug in the new 9,000 and get the new standard deviation. That's totally fine as well. Yes?
Why do people seem to like this one?
They like it because you can find an answer without redoing the whole problem. So
It's just basically a cheat
Yeah.
algebra trick.
it's not really a trick, it's just understanding the mathematical process behind what you're doing when you change it. So they just seem to, for some reason, like this.
It just seems easier.
Exactly.
All right, let's do another problem. Let's try this again. Woo! Who's having fun?
I'm having fun.
Yeah! Sampling distributions of p hats.
Dude, this is what I dream about.
I know, me too. All right, here it is. The superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a 4-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a 4-year college or university. Time out, y'all. Why does the superintendent want to know if we already know the answer is 0.8? Why?
Well, she needs to prove her worth somehow.
She doesn't know, but we know, okay? So let's go with that.
Wait, I thought this was literary irony.
Yes. Now,
Wait,
here's
what?
another thing. There is a very bad typo in this question, Jordan. We should have been told what the sample size is, but it was deleted for some reason. So if you look down on part D, you will see what the sample size is. The sample size here is 125. So select an SRS of 125. That should have been a part of the original problem. You don't have to figure that out on your own later. Okay. All right, guys, here we go. What is the mean of the sampling distribution of p hat? Literally just p, which is 0.8, which was told to us in the problem. Yay! What is the standard deviation of the sampling distribution of p hat? We're going to need to do some calculations here. So the square root of 0.8 times 0.2 divided by 125. Are you guys keeping up? We just need to do this little calculation here. 0.8 is p. The complement of that is 0.2. 80%, 20% works out. And then divided by 125, which is the sample size that we said we're using in this problem. So this is going to be the standard deviation of my p-hat distribution. And what do you get?
0.035777.
0.0358. Perfect. Now we do need to check this strange little 10% condition. So we want to make sure that 10 times the sample size is less than the population. So 10 times 125, that would be 1,250. Do you guys think that the population of middle school students in the large district is more than 1,250? Probably. All right. Again, this will make way more sense in the next chapter. For now, we just kind of go through the process. 1,250 is less than the population of middle school students in large district. What was the question back there?
So are we just, at least for this chapter, supposed to assume always that it's going to be...
Yes, and almost all of your problems are going to say something like in a large city, in a large school, in a large pond, in a large whatever. It'll say something about it being a big place.
And so that's supposed to be inferred that it's
Inferred,
larger than
yeah,
whatever
that it's
it is.
larger than the 10 times n. Yep. All right, guys, we need to make sure that this guy is approximately normal so that we can then do some calculations. So we're going to check the large count condition. N times p has to be greater than or equal to 10. And n times 1 minus p has to be greater than or equal to 10. Both of these things have to be true in order for me to have a normal distribution. What is my sample size that we selected? 125. What is the population proportion p? 0.8. What is 125 times 0.8 or 80% of 125?
That is
100.
100. Is 100 greater than 10? Yep. Now I need to know what is the complement of that. What is 20% of 125? No calculators is needed. 25. How'd you know that, Luke? Absolutely. If 80% of 125 is 100, then the rest of that, the 25, is 20% of 125. Nice job, Luke. So, ladies and gentlemen, that means my sampling distribution of p hat is approximately normal. Let's go. That's a good news for you because that means we can find probabilities. What happens if one of these fails? You cannot use normal CDF if one of these fails. If one of these fails and then you go on to do normal CDF, you're basically just making up stats at that point.
Will you give us a question?
I just might. I'm mean like that. No. Usually this will fail in a multiple choice setting. It'll say which of these conditions fails, and you have to figure that out.
But it won't be.
It would not be that I would give you a part A, B, C, D, and part D is that you're supposed to calculate probability. Part C fails. That would be just rude.
Same thing with the AP exam.
Yeah. All right, cool. So, but since it did pass, let's go ahead and find this
When are
out.
they going to start calling them AP coroners instead of test graders?
I don't know. That's a great question. What is the probability that this superintendent takes a simple random sample of size 125 and it results in a value that is within 7 percentage points of the truth? Okay, what is the true proportion of middle schoolers in her district that want to go to college? 0.8, 80%. So what am I asking you here? To find the probability of what?
That it is within 7 points plus or minus.
Within 7% of the 80%.
0.73 to 0.87.
There you go. So 80%, and I'm asking you to find the probability that her sample of 125 students is somewhere between 73% and 87%. That would be within 7 percentage points of the truth. So, in probability notation, here's what you're looking for. The probability that her p hat is between 0.73 and 0.87. That's the notation that goes with the problem. Okay, you are so excited because you have a normal distribution. The mean of this distribution is 0.8. What was the standard deviation of this distribution?
0.0358.
0.0358. So let's just think about that for a second. If I go from 0.8 and I go up one standard deviation, I'm at 0.8358. Do you guys see that?
Yep.
If I go another standard deviation, about where are we?
0.87.
0.87. And so if I go down 2 standard deviations, about where would we be?
0.73.
0.73. So it kind of looks like, you guys, that I am about 2 standard deviations away from the true value in the middle, 0.73 to 0.87.
Making the answer 4.
Without doing any calculations on your calculator, does anyone remember what percent of the data is within 2 standard deviations?
75.
68 blank 99.7.
Oh yeah.
68 68 95 99.7. This should be really close to 95%. We're going to go ahead and plug it into normal CDF. Lower boundary is 0.73. Upper boundary is 0.87. The mean of the p-hat distribution is 0.8. The standard deviation of the p-hat distribution is 0.0358. And Zane has been saying for 87 years that the answer is 0.9495, which is so close to 95%.
Oh yeah.
It's almost like this whole year is becoming to come together. Ah.
Is the unit after this gonna be like?
Oh, this is like, we're going to be doing like the same thing for the next 4 months. It's going to be like, yes, and yes.
Miss Lakey, when are we going to
This
start
is
doing the
great.
circle walking?
Oh man, I worked circle walking all
we're
day
going to
every
walk
day.
in circles.
To be great.
7 circles every day.
Huh?
Why?
Yeah. All right.
We have to lose our
Let's
minds
look
and
at
our
a
guys
couple
the rest
of
the staff
pictures. Now, this is a little bit difficult to see, but I want you guys to, I don't know if you can see these numbers, but we're looking at these numbers that are below the graphs. We're looking at the P and the N. How does the P and the N affect the standard deviation? Specifically, how does the P and the N affect the shape? What do you guys notice about the top left? What is the shape of that distribution?
Skewed right.
That is skewed right. Now the P, I don't know if you can see it on your paper, but the P is 0.1. The N is 25. What is 0.1 times 25? It's 2.5. Is that bigger than 10?
Yes.
No. So N times P is not bigger than 10. What would be the complement though? It would be 22.5. And that one would work, but the N times P is not bigger than 10. And guess what? We ended up with a right skewed. Okay? So, if N times P is not greater than or equal to 10, the sample distribution of P hat will be right skewed.
And let me guess, if the complement isn't, it'll be left skewed?
Well, let's just look. Do you guys see a left skew graph anywhere?
Yeah.
Which one? The one right below it. P on this one is 0.9. N is 25. 0.9 times 25 is 22.5. So what is the complement of that? 2.25. So on this one, N times 1 minus P does not give us greater than 10. So if N times 1 minus P is greater than or equal to 10 is not true, then the sampling distribution of P hat will be left skewed. Now, the rest of these. This one is really close. These two right here, the middle right and bottom right, they're kind of close to being skewed. But if you look, it's 0.1 times 100. That would be exactly 10. Okay? So that's where it's close. Basically, guys, as P is getting closer to 0.5, then your sample size can kind of be a little lower. But if P is out there on the edges, you're going to need to make sure you have a higher sample size. Okay? So when P is close to 0.5, N can be smaller.
College Board just started sending me scam emails. Like they've sent me spam
Me
before.
too.
I just texted
All right,
you.
guess what? We have a pop quiz. Are you ready?
Du hast 2 Minuten.
Here we go. We have plenty of minutens. Here we go.
Nein, du hast nur ein.
All right. What is the sample mean notation? Sample mean. What's the notation for sample mean?
M.
X bar. What is the sample standard deviation?
X.
S sub x. What is the sample proportion?
Yeah.
P hat. What is the population mean? Mu. What is the population standard deviation?
The other one.
Sigma. What is the sample size? Little n. What is the population size? Big N. How do you notate the mean of the sampling distribution to P hat? Mu sub P hat. How do you do sampling distribution standard deviation?
The sigma.
Sigma sub P hat.